I'm recording now, so no names. Yeah. Come here and get it. It's over here on this. Anybody else need it? Okay. We'll start in a minute. Hold on. All right, so whenever you start doing a set of questions, where do you think you should start on a packet like this?
On one.
And you think you should start on one? I would agree. I would disagree with you.
Start with last.
You start with the last? No, I would disagree with that too. I would start with the directions. That's where I would start. It sounds, oh, wow, duh. But you know what? I bet you a lot of kids didn't look at the directions. Could somebody get him a copy or share with him their copy so that he can see what's going on? I hate to have a visitor not know what's going on. All right, so with the directions tell you, they answer one real important question. They answer two questions. The first thing, anytime you try to solve a problem, and this goes for math, it goes for any problem you do. It's not just science, but it's certainly true for science. First thing you do is you ask, what is the question? What are they talking about? What do they want? So part of that is you have to read, and then you have to phrase it in your own words. If you don't understand the question, then you're kind of wasting your time, right? Or you're to guess, right? I mean, what are we doing if you don't understand the question? So you always start off with trying to understand what the question is. The second step is, of course, you have to answer this question, which is, what do I know? What is it that you know? Well, you've been taught a lot about osmosis and diffusion. A lot. Over many, I think it's something now we're up to 3 hours, right? If you look at it, I think I've sent you 3 videos an hour each, most of which you've done in class. Those of you that were absent, you have a lot of video watching to do this weekend. By the way, tomorrow I'll have another set of questions for you to answer. So what do you know? Well, I'm not going to write down everything you know, but you have some background information on diffusion osmosis. And then you got what? What is the other place you're going to find stuff that you've been told? The stuff you've been told. Well, you don't have notes on a test. So you have directions. The directions tell you information. So let's go ahead and take a look at that. What do they tell you in the first paragraph of the directions? Anybody? So you have a membrane, you have a beaker. What's the thing that they highlighted? They underlined it. So we know the solvent is water, right? Is water, and we knew that. So it really wasn't a big piece of information, but still, it's information. And they tell you to draw some arrows in which direction they're moving, right? So those are the directions. But then they give you 3 bullet points. What are those 3 bullet points? What's the first one they say? So it's permeable. What does that mean? What does that word mean, permeable?
It can go in and out.
That's right, it goes in and out. So it means it's, somebody looked it up and said it was porous. So it allows the material through. Do you agree? So it allows the material through. That's what permeable means. What things does this membrane, are all these membranes going to allow through? What are they? So glucose, can I put GLU?
Yeah.
All right, so glucose, potassium, Na plus or sodium ion, the 2 ions. So wait, don't forget water. That's important. You got to know if it's permeable to water. Water, then iodine, right?
X and Z.
And this stuff, this X and Z. Can I tell you that one of the big things that people had trouble with is they got trouble trying to figure out what X and Z were? Does it matter what X and Z are? No, it does not. X and Z are variables, man. They're just anything. They could be anything. It's just they're molecules that are dissolved in water, or atoms that are dissolved in water. Are we clear? But what do you know about X and Z? The one thing that's important is it what? They can pass through. So that's important. The next thing is, what there's stuff in it that's impermeable. What does impermeable mean? Can't, right? Can't pass through, right? Can't pass. We're all good with that? And I made the P capital, not because you're supposed to, but just so that you can see that permeable, impermeable, they're just opposite of each other. Are we okay with that? Im means not, by the way. In, im, etc., right? There's many different prefixes that mean the negative. Are we good? All right, so what are the things that are not permeable? Starch and why? Those are the two things that can't pass through. So if you see it in there or outside or whatever, it's not going to get through the membrane. Those are really important pieces of information, aren't they? All right, there's another piece that everybody gets confused about. Iodine, what does it say about iodine?
When iodine and starch mix, they create a blue black color.
That's right, it is. Starch, and what happens to starch? What happens?
They create blue black.
Bluish. Oh, there's no E in bluish, sorry. Bluish, black, purple, or purple, black color, right? What do we call something that changes, what do we say when something tells you, hey, by color change or they glow in the dark, it tells you that something's there, a change is happening. What do we call it? No, chemical change is when something changes, that's true. But what is it when something tells you that something's present or that it tells you something in the back? Indicator. The word is indicator. One person in each class has gotten it so far. So iodine is an indicator. It indicates what? What does it tell us? Remember what an indicator is? It's like a signal, right? Like a turning signal. Like when your mom and dad flip the switch in the car where if the light on the left side of the car in front of me is flashing, what is that telling me? That they're going left. So they're signaling, they're indicating, right? So now the colors change. The color changing tells us what? What does the color change tell us?
The two are bonding with each other.
You're missing the obvious. It's obvious. Does it tell you anything about that? Mm-mm. I'll give you a second. This will be one of the fast breaks, I promise you. Go ahead, talk amongst each other. Figure out what is it that it's indicating. Involve our visitor, please.
What's the question again? What is it indicating?
What is iodine an indicator for? What is iodine? Discuss it with your group. Explain why you think it's that way. Hurry, quick, because we're in a
Starch. Because they change. Because they make the color change.
all right. Let's not use duck because people get upset with it. But although I did use it a minute ago, but I was using it in general. I wasn't using it to anyone, right?
Yeah, I felt very offended.
All right, stop playing. All right, are we all good? No, you don't see it? You don't see it? Ledford, oh, sorry, didn't mean to use your name. Could you explain to us what the iodine is indicating?
Starch.
Why do you say that? Explain it to them because they don't understand.
It indicates the starch because it makes color change.
So when does the color change?
When they mix together.
When what mixes together?
Iodine.
Right. So if I add iodine to a solution that has starch, what's going to happen? So that change in color is telling me what? The starch is there. just like the switch that your mom and dad flipped to turn left is telling other people that you're about to turn left. This color change is telling you there's starch there. So it's indicating that starch is there. So it's an indicator for starch. That's what iodine is. One of the things it is, anyways. Are we clear? Are we good? Can I move on?
Yeah.
By the way, iodine is yellow normally, but when mixed with starch, it turns blue or black. All right? That's what they tell you so far, right? And what are the hints they tell you? What are the hints could a book or a test maker or an ACT company, what can they tell you for hints on how to solve these problems? What do they tell you? Have you seen this before? These kind of questions before? Where have you seen these questions before? Some people say, no, it worries me. You have seen them. Where have you seen these kind of questions before? From your notes? You know, didn't I tell it to you yesterday? Do you want me to pause this and rewind and show you where?
No, 5 questions.
The 5 questions, that's right. There's only 4 here, but there's 5 questions you always have to ask. I don't make these things up. There's always those 5 questions you got to think about. I really don't think some people took this homework seriously. I think that that's part of the reason that there's so much angst about this. There's people right now laying their heads down, not really caring, and it just concerns me. But we'll go on. Number 1. Let's take a look at problem number 1. We have a drawing. I'd love to have your answer, but you know what? I'm less concerned about the answer, and I'm more concerned about what? What am I really concerned about? That you understand the process. If you understand the process, then no matter what question anybody gives you, you're going to be able to answer it as long as it's a fair question. We're going to remember that this is glucose, right? All right, so you have a series of questions you have to ask yourself. Problem one has 5 or 6 questions. Question 1 is what?
Is the membrane? Can it go through?
Can it go through? Is it permeable?
Yes.
Yeah, so it is. How do you know it can go through?
Because the directions said it.
Because the directions told you, right? So it's not like you have to memorize it. But sometimes, I'm going to warn you, sometimes they won't. Sometimes they'll tell you it's oxygen gas, and they'll assume that you know it passes through easily. So be careful. The more complicated the question, the more advanced the question, the more they expect that you know already. Okay? So number 2, will glucose diffuse?
Yes.
Yes, it will. How do you know it's going to into the cell? And that's correct.
Because the outside of the cell has more, so it's going to...
That's right, because there's a high and low, right? Excellent. So you guys got the easy, simple diffusion well down pat, right? That's good. We're making progress. What is the percent of water inside the cell at this point? 90% water, so I'm going to put 90% water. Can you guess how many people on a test put 10%? About half.
Because...
About half the people, they're just going to see, they're going to, what they do, I can tell you what they do. They see what percent, and as soon as they read percent, they're thinking their brain shut down, and they see, what do they see inside the cell?
10%.
10%. That's it. 10%. Boom. Next question. And everybody does it initially. It's your brain does it naturally. It's a normal reaction. Your brain is really designed to look for patterns and similarities. And it sees percent on the question, it's going to look at percent on the answer, your brain's going to go for that percent. You got to stop yourself and think, is this the answer? What are you going to do? You're going to ask yourself, what are they asking me? Yeah. Any other question? We're good? Let me pause it for a second. Yeah, question? Oh, yeah. What is the percent water inside the cell? Go ahead.
Yeah, I put 100% because I thought the inside, like it was more water than inside.
Well,
you got to take 100 minus 10 because there's 10% solid.
yeah, if they tell you there's 10% glucose, then that's part of the pie. That's 10% of the pie, right? And then there's 100% left, and there's out of 100, 10% is glucose. That leaves the rest water. Does that make sense?
Yeah.
Yeah, I know, that's why we go through it, right? That's why we discussed it. So I'm glad you're making a mistake now so that you don't make a mistake on the test. Question?
I kind of forgot. Can you tell me the difference between diffusion and osmosis?
Well, we'll talk about it in just a second. So diffusion, in this case, diffusion is the process where things go from high to low. What goes from high to low? The solute. Could someone close the door, please? When the solute goes from high to low, we call that diffusion. We'll talk about osmosis in just the next question. Will osmosis occur?
Yes.
Why do you say yes?
Because it's more water in the cell, so it's more out of the cell.
I can see someone thinking that, especially if they didn't listen to what I had told them initially in their notes, or they didn't study those notes, or think about it, revise them, recite them. Because the devil's, they say the devil's in the details. It's the details that get you every time. So osmosis is the moving of high concentration water, low concentration water. You're right on that. The part that you're missing is that osmosis happens only when the solutes can't move. So water moves when the solute can't. So that's really important. And by the way, water moving is called osmosis. Water moving following its concentration gradient. So when we're talking about osmosis, will osmosis happen? No, because equilibrium will be reached by the solutes moving across the membrane. Glucose will move until you got about 50-50 on each side. That's it.
So, osmosis only happens when diffusion can't?
That's right. Are we good?
Yeah.
All right, let's go ahead. Who said no? What's the issue? Tell me.
Because I was watching a video yesterday, and the lady was like, osmosis will occur because it's more water inside than the outside.
That's true if the solute can't move. If the solute's going to move, then you're not going to get osmosis. Does that make sense? The key is that the solute has to, if the solute can't move, the solute's going to move before water gets a chance to move. Does that make sense? Okay, so let's move on. All right. Will osmosis occur? No, it won't occur in this case. All right, now 5. The movement of water will cause changes in the cell shape and size. Will this cell shrink or swell? Why?
Shrink. No, it's gonna stay the same.
No, it's gonna swell.
It's gonna stay the same because osmosis is not even gonna happen.
It won't happen. Osmosis won't happen, so there's not going to be any movement of water, so there's no change in shape. Oops, trick question.
Why you ain't put or nothing?
It wasn't me. Are we all good with this?
Yeah.
So the key is that when you're going to get osmosis, it's going to happen when neither is the answer, because the glucose is going to move. Now, normally, if this were, let's say this is, which is this? Is this a hypertonic solution? It's a hypertonic, that's right. It's hyper because outside it's 90% glucose and inside it's 10% glucose. And so 90 is bigger than 10, so it's hypertonic. Can you imagine for a second if you put it in a 90% glucose solution and the solutes could pass through? Could you imagine for a second what would happen if glucose could not pass through? What would happen? Put it in a hypertonic solution. The cell would shrink. The water would move out, right? But that won't happen because glucose is going to rush in. Are we good?
Yeah.
All right. Now, the story's more complicated than that, but at your level, these are the kinds of answers that are going to get you right answers on all your tests. You won't have to do, like in AP Biology, you'll calculate partial pressure, and osmotic pressure, and there's all kinds of details on everything you have to do. All right, osmotic potential is what you'd have to try to figure out in AP biology, but we're not going to do that here. So, will glucose diffuse? All right, let's look at another problem, problem 2. Let's move on to this so we don't get it confused. Problem 2 says, will glucose diffuse if you have a situation like this? And you know, glucose will diffuse unless they're what? What's the only, in this case, unless they're the same concentration, that's right. Well, they're not the same concentration in problem 2. Outside is 60% and inside is 10%. And inside is 60%. Now there's 2 solutes. Oops. 2 solutes? What are we going to do with that?
Only one could go in.
That's right. That's really the key. Only only glucose is going to move in and out. Starch won't move through, will it? How did you know that? They told you the directions. Do you have to worry about glucose when it comes to osmosis? No, because it's going to move. They're going to move back and forth, right? These two. What's going to happen with glucose? In what direction is it going to move? Outside to inside or into the cell, right? And it's going to move until it reaches equilibrium, right? So there'll be equal concentration of both sides. This inside will go up and outside will come down until you come to some middle ground. Let's say it's, I'm just going to make up a number. Let's say it's 25 on each side. That wouldn't work, right? I don't know. Let's just say it's 25. 25% on each side, let's say, right? At the end, once this all reached equilibrium. Are we good? Let's say that happens. Okay. Well, what happens now? I just said that everything is really much more complicated than I'm stating. We're actually talking about it very simply. All right. So what happens with starch is starch can't move. So it won't diffuse. So what has to happen now? Osmosis. And so now osmosis means the water's going to move. So which side, is this a hypotonic, hypertonic, or isotonic solution?
Isotonic.
Wow, why would you? Oh, I see. I think I understand why you think it's isotonic, because you're looking at 70% outside, 70% inside.
Yeah.
Oh, yeah, I can see that. No. Because the glucose is going to move in and out, so they'll become equal. So they'll, what are they going to do? What can you think of? Can you imagine that the glucose is, because they're diffusing, they're going to neutralize each other. They don't have to worry about it because they're going to be equal, right? The glucose will be equal. But what is not going to be equal? Starch.
So it's hypotonic.
So it's hypotonic, is right. So it's hypotonic. So even though glucose, you're right, if you look at it as a total percent of the pie, that it's 70 outside, 70 inside, you're right. But since glucose can pass back and forth, right, the molecules, they will until they get to equilibrium. And so that means that it's actually a hypotonic solution. Once the glucose goes to equal on both sides. Does that make sense?
A little bit.
Let me draw it out. Can I draw it out as a pie? Let me look at it as a pie. Let's look at it before. Let's do 2 circles. Let's do a pie before glucose diffuses, and a pie after glucose diffuses. Can I do that with you? Can you understand that? So before glucose diffuses, what's going to happen is you're going to have what? 10% glucose, is that right? And then there's like 60%, something like this, 60% starch. And then the rest of this was water, right? Everybody okay with that? That's kind of what was happening there. Now outside, after, rather, I guess I should do it outside as well, or maybe that's not a good idea, I don't know. Let's go ahead and do outside. Ooh, that's a weird circle. So outside was what? 60% glucose, so 60%, that's way too, that's much more than 60%, but who cares? You get the idea. Starch, oops, glucose, sorry. Glucose, and then we had something like 10%, right, which was starch. And then the rest was water, right? That's before. Do you agree? So you're right, the percent water was the same for both in the beginning because the percent water was, it was 70% other stuff and then 30% water. Do you agree? So the solution was I guess you can consider it isotonic if you really want to get nitpicky. But let's go on and let's look at after. What happens after? Let's talk about inside. The same thing's going to happen to the outside. But let's go ahead and take a look at inside. What's going to happen after?
35%.
So the glucose is going to be the same. And so now instead of 10%, it's going to be something like, I don't know, something like that, 35%. So the inside is going to go up, right? 35%. But on the other side, it's also going to be 35%. Does that make sense? And the starch is still going to be 60%. And in here you have what? So this went down. The percent water went down, didn't it? So instead of 30, let's say it went to, I don't know, let's, so 20.
Where did you put 70?
Because the 60 went into the cell and the 10 went up, right? And that had to come from somewhere. Starch can't go anywhere, so that's not coming from there. That's still starch. That's staying 60% because it can't go anywhere. Now the other circle, the outside, what happened to the outside? That's right. And it's also 35%. Again, the pie drawings are horrible. And it's now it's only 10% starch now though. So that's starch, right? And this is what? This is what? This is glucose. Now what is it inside? It's about 20, more or less, right? But starch on the inside, if we take a look on the outside though, what is all this?
Water.
That's all water. What percentage is it now? If 45% is glucose and starch, what is water?
You just make the screw my whole paper.
55%.
Yeah, 55% water. So now the outside became 55% water, the inside's 20% water. So what is it? Outside is 55% water, inside is 20% water. Is it hyper, or iso? It's hypotonic. Why? I know you're saying hyper because you're thinking the percent is bigger outside. It's the percent solute, guys. The percent solute is higher outside. The percent solute's smaller now outside, isn't it? It used to be that outside it was only 30% water, but now it's 55% water. Inside it used to be only 30% water, but now it's 20% water. Do you see that? Because the glucose rushed in and made outside the water become a bigger percentage of the pie outside and the smaller percentage of the pie inside because glucose rushed in. Is that clear? So you could do all that. You could be thinking about all that and think about the pies, and right? It's kind of headachy, right? It gives you kind of a, ooh, this is a lot of complicated stuff, right? Or you could do the following. Or this is an option for you, or you could do the following. You could say, well, glucose is going to equal out. And so the only thing I got to worry about when I'm worrying about osmosis is what? The stuff that doesn't move. So if I worry only about the stuff, now can I come up with a realistic percentage? Yeah, I could go ahead and figure out the percentage. Do I really need to know the percentage to know which direction the water's going? Do I really need to go and try to figure out all these percentages and draw out all these pies and think about how water moves? No, all I gotta do is say, look, I can ignore this because these two are gonna be the same. They cancel each other out, right? The only thing I gotta worry about is starch. When I'm talking about starch, if starch is highest inside, then water must be lowest inside. If starch is lowest outside, then water must be highest outside. And if water's highest outside, we call it hypotonic. Because that means the solute's lowest, right? If the water's highest, the solute's lowest. You have to keep remembering they're opposite of each other, as they're inverse relationships. Are we clear on this? I know it's confusing, but just come up with that rule. All I gotta do is worry about starch. Where's the solute? What solute am I talking about? The one that doesn't move, right? When I'm talking about osmosis. Because the one that does move will move. I don't have to worry about that one. That one's gonna sort itself out. Which one's the one, which one's the one that doesn't move? It's starch. And where's starch the highest? Inside. And if it's highest inside, the solute's highest inside, the solute's lowest outside, what is it? Hypotonic. And when you have hypo, what direction does the water move? Water does what? It moves into the cell. That's all you gotta know, right? See how easy that is? Say that again, I can't hear you.
Will the starch always be highest inside the system?
No, and in fact, we'll see in some examples in the problem set. I really wish you guys would do the problem set before you come in. I think you'd end up, even if you don't get it right. I know it's confusing, but even if you don't get it right, just reading it and trying it will help.
I did mine.
I know, I see a lot of you did it. And it helps, doesn't it help?
Even though I got half the stuff wrong.
Yes, getting it wrong helps. Being wrong helps. Because then when we're discussing it, we have something to discuss. All right, let's go on and do the next one. What is it? Problem 3, right? All right. We're going to do a bunch of these, so hopefully by the time we're done, and by the way, I already did these with the other class and actually approached it differently, so I might actually post both the videos because this actually turned out to be a very interesting discussion. At least for me it was. I hope it was for you. It seemed to be like you guys were engaged. All right, so here we have this cell, and you got 10% potassium, 10% sodium, 10% starch. All right, outside you have 100% water. So what do before I even do anything, what are you thinking outside is? Only water. So is that hypo, hyper, iso? It's a ton of water, but what do you call it? It's hypo. It's perfect hypo, right? There's nothing else out there but water. There's zero solute, right? In the beginning. So this is definitely hypo. Do you agree? All right, so which directions is potassium going to move? Outside. And sodium, which way is it going to move? Outside. Why? Because it's 10 and 10, but what's outside? 0. And if starch can move, where would it go? Out, but it can't move. That's right, it's not going anywhere. So how is this going to come to equilibrium? How are you going to get starch to be, the concentration of starch to be as equal as it could possibly be? What's going to happen? Water, osmosis is going to happen. And which direction is osmosis going to happen since you have a hypotonic solution? Into the cell. So water is going to move in. Do I have to worry about the other two? No, because they will move on their own. The potassium and sodium will move on their own. The one that water will move to try to equilibrate is that starch. Does that make sense? So 10% will become very, very small. It can never get to 0. It can never get to pure water, right? But it's going to try to get to get as close to equilibrium as it could possibly do. If this was a real cell, who knows? Maybe the cell would burst, right? All right. So do we understand that? So you should be able to answer the questions now that we went through that. Anybody have any questions about problem 3? Concerns? All right. Following the same rules, every time you do these, it'll be the same solution, the same. All right, problem 4. We have a cell. It's 38% glucose, 15% sodium, 3% potassium, and 5% starch. Right? And then outside we have what? 40% glucose, 20% sodium, and 1% potassium. How much? What percent starch outside? Nothing. Well, quickly, we know, what do we know about glucose, sodium, and potassium? So what direction is glucose going to move? Into the cell. What about sodium? Into the cell. And what about potassium? So that's 3 answers right there, right? Real quick, easy. I don't have to worry about those for that's diffusion. That's the diffusion that's happening. I don't have to worry about them for osmosis though, right? For osmosis, what do I have to worry about? I have to worry about starch because starch can't move. So it's 5% inside. What percent starch outside? 0. So what is it outside? Hyper, hypo, iso? It's hypo. Right? There's more water out. There's 0 solute of starch outside. So this is a hypotonic solution, right? Hypo. If it's hypo, what direction is the water going to go? Into the hypo means water goes in. Hypo means water goes in. Are we good? I think I've been saying it the same each time, right? So now there's a trick. Oh, which one am I doing? I'm doing, the number 4, right? So there's a trick they threw at you. They said, okay, we got this. The salts and the glucose and the sodium and the potassium, they're all in equilibrium. They got the salt, the water's rushing in. About an hour after you let this equilibrate, so you're going to put iodine in. I'm going to put iodine in yellow. Why do I put iodine in yellow? Because that's the color of it. So iodine's kind of a yellow, darker yellow than this, but that's fine. Iodine's yellow, and you put it in there. You put drops of iodine in there. And it spreads through diffusion around here, all over here. Does iodine cross the membrane? Yes. So iodine's going to go into the cell, right? Because it's high out here, and it's whatever the concentration is, high out there, and it's 0 inside, so it's going to move in. What happens when that moves inside? And give you an indication that starch is there, right? And what color is that indication of it? Bluish black. So inside will turn bluish black, outside will be yellow. So that's what would happen in number 6 of problem 4. Do you agree? All right. Number 5. Number 5, they changed it a little bit for you. Not much, but you see how there's not really a lot of ways they can ask these questions, right? They've always tried to trick people because they always want to test to see if you know what you're doing. When I say they, I mean the standardized exam people. But so where's the iodine? Outside. What color is it outside? It's yellow. It's 10% outside. In what direction will glucose move? And what direction is it going to move? Inside. Do I have to worry about it for osmosis? How about potassium? No. Where's it going to move? If it moves, it's going to move inside. Now, Iodine. Starch doesn't move, but iodine does. Where's iodine going to go? Okay, inside. So outside it's yellow. What color is it inside? Right. So let's go through and answer that question. Number 5, on problem 5 says, what will the initial color be of the solution immediately after you put it in the cell? The iodine solution, what is it? Initially in the cell it's white because they tell you in the white starch is white. Where do they tell you that? Look at problem 6 or problem 4, question 6. They say a starch solution is white. So the starch solution inside the cell is white. In the beaker, initially, the water is what?
Clear.
No? Yellow, because there's iodine in the solution here, right? It's actually a darker yellow, but it'll be good enough. And what is the final color of the solution once osmosis happens after several minutes? What happens? In the cell, it's purplish black. Outside the cell, in the beaker, it's what? Yellow, because starch never leaves, right? But the iodine goes in. And people had a lot of trouble with that question. I got a few emails last night about it. I wanted you to struggle. Let's go to problem 6. Problem 6, oh man, there's variables. Now I'm getting a headache. As soon as I say X, Y, Z, all I ever hear from kids is, this is too much. Really? It's too much? Isn't it the same stuff? Isn't it really the same? If you know the process, then variables are just a little bit of a tweak to that process. The process is the key. Outside is 3%, right? And outside is 2% starch. Now the starch is outside. Is starch going to move? No. Okay. Is X going to move? Yeah. What direction is X going to move? So X is going to move outside. And is Y going to move?
No.
No. Why not?
It's purple.
Is Z going to move?
Yes.
So is it going to move where? Outside. Good. Is starch going to move? No. Is glucose going to move? Where is it going to move? Inside. You see that? So now, where is the solution of the ones that can't move? Now I've just got rid of the ones that are moving. I know what direction everything's moving. I know the starch isn't moving, and I know Y is not moving. Which side has the higher concentration of solute? Where? Which side? Inside. You have 5% versus what? 2%. So what's going to happen? Osmosis, first of all, because neither one of them can move. But what solution is this? Is this hypotonic, hypertonic, isotonic? Hypotonic. Why is it hypo?
Because it's more solute inside.
There's more solute that can't move inside than there is outside, so it's hypotonic. What direction does water move when it's hypotonic? When the solution is hypotonic? Where? Inside, moves into the cell. Water flows in because remember, it's trying to dilute. The whole point of osmosis, the whole idea is that whole room, space for movement, space to be in there. There's more space. Yeah. So that's what's going to happen. The water's going to move across. Are we good? All right. So let's see. If you're told that one of the molecules XYZ was a polysaccharide glycogen, would you guess if XY or Z was a polysaccharide glycogen, which would you guess would be the glycogen and why? The Y, because it can't go through. That's right. Because you should know by now that glycogen is really big, right? And big things, do they go through a membrane easily? No, they don't. And you have to think about what polysaccharide is. All right, let's look at number 7. Number 7, problem 7, last one in the series. And there'll be another set for you tomorrow. We'll go over it one more time, and then I'll give you a practice test on Monday or Tuesday, and then we'll set the schedule. We'll schedule your actual test on Thursday. All right? Problem set. What is it going to be on? Passive transport, which is all this stuff we've been talking about.
When are we going to be given the packets, because we're gonna need the.
Tomorrow. I'll bring it to you tomorrow. All right, problem 7. Let's draw the beaker. Let's draw the water. All right, so last question. So we can do this in a minute. I think we can do it in a minute. I think we can. And then starch. I know we said we didn't want to go down the wire, but I think everybody wants to know the answer, right? 13% iodine. Uh-oh. And 2% starch. What color is it outside? Is it?
White.
What color is it outside? Purple black. Why is it purple black? What do you got? Because you start off with inside being white, you start out with outside being black or purple because you have iodine and starch together in here, and in the beginning you only have starch inside. Then what happens does Y move across the membrane? Does starch move across the membrane? No. Well, so now that none of this is moving, is this hypotonic or hypertonic?
Hyper.
What is it?
Hypo.
Well, first of all, remember, you got a problem. Yeah, somebody got it. Somebody already figured it out. But I'm sorry, I didn't hear you. Because iodine's going to go in and out until it gets to equilibrium. So which ones are you worrying about? Y and starch and starch. Y and starch are the only two. Inside you have 10%, outside you have 2%. The iodine's going to equilibrate, and so what you have is a hypo solution. Right? Everybody good with that? So you have a hypotonic solution. And so now water will move in. Of course, water will move in. And what will be the inside after it's equilibrated? Blue-black. Starts white, it's going to turn to what? Blue-black.
I thought it said purple.
And by the way, here's a bonus question for you as you leave the room. Are these problems examples of active or passive transport? Passive, no extra energy is necessary.